So I have got some images on the board here, and the reason I'm showing you these images is because these are some curves that actually, as you can tell, appear in many places in real life. And the places these appear in real life are mostly what you can see is things that are like hanging chains, okay? These things that we've got here are like heavy ropes, or things that are actually have got quite a lot of mass, like this one here. This is sort of, it's not like a light string, it seems to be made of metal. We've got these parts of this suspension bridge that we've got here as well. And even just when you look outside at pylons, I don't think we can even see any from out of here because we've got that nice view of the park. But the way that these metal wires actually hang are a particular type of curve that we will not have come across yet. Many people sort of think to begin with that they might be quadratics, but they're kind of heavier than a quadratic. And they are a specific type of curve that comes from the hyperbolic functions, the hyperbolic trigonometric functions, which is what we're going to have a look at today. Yeah. And these hyperbolic trigonometric functions, they are related to the trig functions, but they are a bit different to the trig functions as well. The only one I haven't spoken about is these arch functions that we've got here, these arch shapes. They're also going to be related to these hyperbolic functions that we've got. So it's just a bit of like a connection to why these things have been studied. They do actually appear in real life, because on the next slide, when I start telling you about what they're all about, you're going to be like, huh? Like, why did someone come up with this definition? So over the course of this topic, we're going to be looking at hyperbolic functions. I've called this chapter 6A because the second half of chapter 6 I like to do with chapter 3, which is called methods in calculus. And methods in calculus is everything to do with differentiation and integration. So we're not at a stage to be able to do the second half of this chapter. And I actually think the second half of this chapter merges really, really nicely with chapter 3. It flows on really well. So we're just going to be looking at the definitions and solving equations that include hyperbolic functions. So we're going to find different definitions and purposes of hyperbolic. They're actually called hyperbolic trigonometric functions, but we just shorten it to hyperbolic functions. And I'll tell you a bit more about what these things are in just a second. We're going to investigate their inverse functions, how we manipulate them, solving equations, differentiating, integrating, all of that kind of stuff as well, okay? So I'm going to just really just dive in straight away and tell you what these hyperbolic functions actually are, okay? This hyperbolic function that we have here, it is the hyperbolic cosine function. So that's why the h is added in here. And it is called cosh x. If we're going to say that out loud, we would say it is cosh x. But really the posh way of saying this is the hyperbolic cosine function. You just don't find mathematicians saying that out loud because it's a bit of a mouthful. And the hyperbolic cosine function, or cosh of x, is defined as e to the x plus e to the minus x over 2. And you may sometimes see that written as just a half of e to the x plus e to the minus x. This is a definition that you just need to know and have committed to memory. And as I was just talking about the complex number chapter from chapter 1, these things are actually going to pop up in chapter 1 as well, but they don't refer to them as hyperbolics in chapter 1, but you will see this relationship to do with complex numbers as well, being connections with trigonometry. So this is a fundamental thing that will connect together many chapters. And then the hyperbolic sine function, which is actually weirdly said as shine x, so instead of sine x, it's shine x, is the same as cosh x, apart from instead of it being a plus in the middle, it's a negative in the middle. So shine x is a half e to the x minus e to the minus x. So using these definitions, I just want us to be able to say what we think the definitions of these four functions. I'm going to say these functions again later on, but this is sech x, so it's like it's S-E-T-C-H, sech x. This is cosech x. This one, there's a couple of different ways that you can say this one. Some mathematicians say tanh x, but I like saying the other way of saying it, which is than x. So it's imagining that instead of it being tan, it's than, to say that it's a hyperbolic tangent function. And this one is just say what you see, it's just koth, okay? So we have cosh, shine, sech, cosech, than, and koth. But you may see tanh people may say tanh, and it means the same thing. So I'm just going to give you a couple of seconds, or not a couple of seconds, a minute maybe, to just see if you can think what these definitions are. Now, they're going to be what you'd expect them to be, okay? Sech is obviously going to be related to, it's going to be 1 over cosh, okay? So just think about what 1 over cosh would look like and write that down. So I'll just give you a few seconds to see if you can have a go. And if you haven't got them, if you're not sure what they are, I do have the definitions on the next page. So if you write them wrong on this first page, don't worry, because you've got the actual definitions on the next page. So have a go at these ones. Okay. So don't worry if you haven't done all of them. We'll just talk through some of these. I've just noticed I've spelled definitions wrong here. Definitions, whatever. Spelled it right the next time, missing an I. So sech, we know, is 1 over cosh, which is just the reciprocal of cosh. So sech is just going to be this one, but just its reciprocal. Okay? It's the same thing with it being the third letter, meaning it's related. So it's just going to be 2 over e to the x plus e to the minus x. Just as simple as writing the reciprocal. And so cosech is going to be the reciprocal of sin x, which is 2 e to the x minus e to the minus x. And then than, well, than is going to be, what do you think than is going to be? Sin over cosh. So every time I'm going to now say S letters, it's going to sound like sh, because I'm going to get it confused. So instead of show, so it's going to be sin over cosh. So I'm not going to bother writing the halves because the halves are going to cancel. So it's going to be e to the x minus e to the minus x over e to the x plus e to the minus x. And there's another form of this that they use that actually doesn't include negative powers here. Can you think about what I could multiply the top and bottom by that would get rid of negative powers?
E to the x.
Good. If I multiply the top and bottom by e to the x, e to the x times e to the x is? Good, e to the 2x. People sometimes say e to the x squared, which isn't true because you're adding the powers. So it's e to the 2x. And what's e to the minus x times e to the x? 1. So it's just going to be e to the 2x minus 1. And then on the bottom, we're going to have e to the 2x. And yeah, the powers would be 0, so it's just going to be 1. So sometimes we see that than x is e to the 2x minus 1 over e to the 2x plus 1. But I'm quite happy with this first form that we have of it as well, okay? And so koth is the reciprocal of than. So I'm literally just going to take both of these and just write them upside down. So it's either e to the x plus e to the minus x over e to the x minus e to the minus x, or it's e to the 2x plus 1 over e to the 2x minus 1, just taking the reciprocal of that we've got there, okay? Yeah, because koth is 1 over than. And at this stage, you just have to trust me that this is what the functions are. And the more that we learn about the topic, you will start to see why it is called shine instead of some other name, and why it is called cosh instead of some other name, because they will have these really bizarre properties that are almost the same as how trigonometry behaves. And I say almost the same because every now and then there is something that's a bit different about them. And it's kind of weird that we're talking about functions that are exponential functions, and we're talking about trigonometry, and we're actually saying how they're kind of close together. They're actually sort of similar. But you probably know that from complex numbers, don't you, about the exponential form, that the exponential form is a combination of sine and cos. So it doesn't seem that surprising. Well, I think it does still seem surprising that there are these connections that are going on, okay? So this is a summary page of all of the things that we've talked about so far. So the hyperbolic sine function, I'm not going to read through all of these bits, just as a reminder of how we say this. We've got sine, cosh, tan, sech, cosech, and coth. But there are a few values here that for the domains we just want to be a little bit careful of. So the only one we need to be careful of is where we have cosec x, and they've said that x cannot be equal to 0. What would be the problem if x were equal to 0? The denominator would be 0, and so it wouldn't be a function because the input value wouldn't have an output. And it's the same thing for the hyperbolic cotangent, or the coth. X cannot be equal to 0 for the same reason that the denominator would be equal to 0. Not quite sure why I've put brackets here. Obviously, we don't need brackets in the numerator that we've got there, okay? So we're going to try and actually just start finding out what these things do and like how we can actually start using them. And we have to find out how we use them before we can find out why we're using them. So we're going to start thinking about equations for hyperbolic functions. And we want to calculate using both the shine button and using the formula. I want to calculate shine 3. So on your calculators, I need to quickly see if I can remember where this is. You would go to option, scroll across to hyperbolic, then press shine, and then press 3. So I'm just going to say that again. It was option, scroll across, hyperbolic, then you select shine, and then you input 3. No. So that's a good question. Arif asked, does it matter if it's in radians or degrees? No, because although it looks like it's a trig function, this is not a trig function. This is an exponential function. And exponential functions don't, it's just an input. It's not degrees or radians. So using the calculator, what did you get for shine 3? 10.017, blah, 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 blah. Okay? Now we're going to see if we can find out what shine 3 is, not using the calculator, but using the formula or using the exponential, the definition that we've got. So shine 3 would be equal to a half e to the 3 minus e to the minus 3, because that's what the definition of shine is, okay? Same thing. You type it into the calculator, that's what the calculator is actually doing, and you get 10.017, blah, blah, blah. Okay, so the next one that we'll try, we're going to write it just in terms of e, so we can't use the calculator for this time, but we're doing cosec 3. Now cosec is the reciprocal shine function, and that's normally shine of x is a half e to the x minus e to the minus x. So this is the reciprocal of this. So it will be 2 over e to the 3 minus e to the minus 3. And so that is it written in terms of e, but I don't usually like leaving the denominator as the messy kind of thing. Even we don't like putting surds in the denominator. We don't like putting all kinds of things like that. So I'm just wondering if we could even just make it look a little bit neater. What do you think I could multiply everything by to tidy it up a bit? Yeah, I could multiply by e to the 3 and e to the 3. It's not going to do an awful lot, but I will get 2e cubed over e to the 3 times e to the 3 is e to the 6 minus 1. I just think it looks a bit better. I just think it looks... Okay, so we're going to try the next one. This time we're going to find the exact value of tan of ln 4. So tan of ln 4, we could use the calculator, but I don't want to use the calculator. I want to show you how this thing works. Now, the definition of tan is e to the 2x minus 1 over e to the 2x plus 1. Now, I'm hopefully wanting to try and get into your brains that when it's with a minus, the minus is the one that goes with shine, and the plus is the one that goes with cosh. So I can tell that this is tan because I've got the minus and then the plus, okay? You're going to start seeing negative and thinking of shine, and you're going to start seeing the plus and you're going to start thinking of cosh. That's sort of how I want you to build up to this. So this is going to be e to the 2 ln 4 minus 1 over e to the 2 ln 4 plus 1. I guess you could have also used the other version of the formula, which is e to the x minus e to the minus x over e to the x plus e to the minus x. You could have used that version and it's still going to be fine as well. So you need to know how to do all of your manipulation with exponentials. What is e to the 2 ln 4? Yeah, so it's going to be the same as e to the 2 ln 4 is the same as e to the ln of 4 squared, which is just going to be 16, because the e and the ln are the inverse of each other. So you just get 4 squared, which is 16. So you get 16 minus 1 over 16 plus 1, which is 15 over 17. And now I want you to use your calculators to confirm that that is indeed the answer. It is the right answer? Yeah. Okay, so we're now going to try and do solving an equation. We're going to try and solve that shine x equals 5. So that means that 5 equals a half e to the x. Is it plus or minus for shine? Minus, good. It's e to the x minus e to the minus x, like this. So we're going to solve this equation. And these equations always have a similar kind of technique that you use. So first of all, I'm going to multiply both sides by 2. So I get 10 equals e to the x minus e to the minus x. And there's a trick of solving these equations that we've got here. Do you think you know what I could do to this equation? Yeah, not multiply by natural log. No. We're going to multiply by e to the x. And what did you say, Sam? It becomes like a quadratic. So we get 10 e to the x equals e to the 2x minus 1. So we multiply by this, and then this thing that we've actually got here is a quadratic. This is a really, really common technique when you have something with one power, a constant, and a negative power of the same thing. If you multiply through by the power, this power that you've got here, you end up with a quadratic equation, or a pseudo-quadratic equation. It's not exactly like a quadratic, it's a quadratic in e to the x. Like this, okay? So you could, obviously this one can't be factorized, so what we're going to do is use our quadratic equation solver with a as 1, b as minus 10, and c as minus 1. And so this tells me you get two solutions. Either e to the x is 5 plus root 26, which is a 10.099 kind of number, or e to the x is 5 minus root 26, which is minus 0.09999. And I just want us to try and think about those two answers there and to try and interpret Is there anything you can tell me about this? Yeah, this one has got no solutions. Why? Good. E to the power of x is always greater than 0, okay? And when you do the equation solver, that's why I wrote it out here to show you that it was negative. Obviously, you can tell 5 minus root 26 has to be negative because root 26 is obviously bigger than root 25. So there's no solutions to this second one. So there are just going to be solutions from this first one. So x is going to be ln of 5 plus root 26, which obviously you could type into your calculator and come up with an answer. But I'm actually not going to do that because we know that in pure maths we often like to have exact values. But obviously, I mean, should we just see what it is? ln plus 5 root 26. The answer is 2.312. Just a number. Nothing special about that one that we've got there, okay? And now we're going to try and think about how we sketch some of these graphs. So I have plotted on the board here e to the x. I've then drawn e to the minus x. I've then on the separate graph drawn e to the minus x and then minus e to the minus x. So how are these two related to each other? What's the transformation and why is it the transformation? It's a reflection in the x-axis because yeah, because it's just the whole graph, the whole thing has been multiplied by -1. So that's why we've got this one. Why have we gone from this shape to this shape from e to the x to e to the minus x? I think I would see it's more a reflection in the y-axis because the input value is the thing that has been negated here. And then the last one is a reflection in the y-axis, then the x-axis, or vice versa, because it is both negated on the outside and in the input as well. So the reason I've drawn these is because it's going to try and help me figure out how I can plot what sin x is. Obviously, you've got graphics calculators, but it's nice to try and think about some of these ways of how we might plot this. So we know that sin x is e to the x minus e to the minus x over 2. So I'm going to take this graph and this graph, and I'm going to add them. No, not that graph and that graph, is it? It's e to the x and negative e to the negative x. It's this graph and this graph, and I'm going to add them together and then divide it by 2. And you can add graphs together by just thinking about what their values are at particular points and adding them together. And I'm going to do that by drawing it onto the board, okay? So I'm going to draw on here. Here is the e to the x, and then here is minus e to the minus x, like this. And because we are adding them together and then halving them, we're actually finding the average of their y values. So if you think about the average of their y values that we would have, well, this is basically going to be 0. So it's going to be sort of down here, really. It's going to come like this, and then up here. Now, the reason it goes through 0, my sketch isn't very good, is what number does e to the x go through? 1. So this must be going through -1. So when I add these together and divide it by 2, I get that it's going through 0. So the sin graph looks like, but is not, it looks like a cubic graph, but it's not a cubic graph, okay? But it has the same S-like shape of the graph that we have there. Just to kind of think about why that's happening, this part of the tail, this part of the graph, oh, sorry, I'll give you a second to draw that first. This part of the graph that I've got here, as x gets bigger, what can you tell me about the y value of this section? It's basically 0. So at this point, this part of the graph is going to start matching the normal exponential part of the graph. Well, half of it. It's never actually going to match it. I've perhaps done it a little bit too close. Don't worry about it. It doesn't matter if it's too close, because it should be half of that. So it's sort of going to be in between. And then when you get to this extreme bit down this end, because this bit is close to 0, it's just going to be half of this bit. So again, I've probably done it. It probably should have been a bit better sort of more like this and the in-between, but it's kind of hard to sketch things, particularly when I'm stood at the board like that. But it's going in between those two graphs that we've got there. It looks a bit like a cubic. And I've said here, is this an odd graph or an even graph? I'm not sure, because I didn't teach you in year 12 for complex numbers. Do you know what an odd or an even function is? Yeah, good. Cos x is an example of an even function, because when you have a cos graph like this, it has symmetry about the y-axis, okay? And when I say that something is an even function, that means that f of x is the same as f of minus x. It's even because if you go to the right with the positive values, it's exactly the same as if you go to the left with the negative values. And an odd function, an example of an odd function is actually the sine graph, because the sine graph, you go to these positive values, these are the positive values you have, but if you go to the negative values, it's the same, but negative. So the way I would write that is that f of x is equal to minus f of minus x. This is like going beyond what the what's A-level further maths is about, but it's worth thinking about what these actually mean. So let me just quickly do one more thing. Even functions have reflective symmetry about the y-axis. Odd functions have rotational symmetry about the origin. That if you go to the right of the origin, it's the same as going to the left, but negated. Even functions, if you go to the right of the origin, it's exactly the same as if you went to the left of the origin. So in this particular case, you are correct. The sine function is an odd function. Can I go on to the next bit? Okay, so we're going to try and draw cosh x now. So cosh x is the average of e to the x and e to the minus x. So that's e to the x and e to the minus x. I'm going to plot both of those. And they're crossing both at 1. And so because it's the average of those graphs, it's again going to be like in between both of them. Can you tell me where it's going to cross the y-axis? At 1, yeah, because you've got 1 and 1 for the other one, so it's still going to cross here. And so you get this kind of shape. Because it's the average of these two graphs. You get this kind of curvy U-shaped sort of thing. And it crosses at 1. And how does that link to what I showed us right at the beginning of the lesson? How do you think this could link to what I showed you at the beginning of the lesson?
It looks like the chains.
Yeah, it looks like a hanging chain, okay? This is how ropes, chains, anything that is heavy and hanging as like a piece of string or a bridge, this is how things naturally hang. They hang according to the hyperbolic cosine function. They hang like this, okay? They don't hang like a parabola. They hang like this shape that we've got here. And so do we think that cosh is going to be odd or even? It's even because it's reflective around the middle that we've got there, okay? And you can kind of think about how that would work here. If you switched this with minus x and you negated this one, you would still have cosh. It would be the same function because it doesn't really matter which direction that you go in. So cosh is an even function here.
So you see in regular maths,
Yeah.
you do like modelling with quadratics and stuff. Would modelling with this be natural?
It depends on what the thing is that you're modelling. So the things we model with quadratics are usually projectiles and things that in real life do follow quadratic paths. You wouldn't use a quadratic to model this kind of curve. If you're going to be doing engineering at uni, which many of you are, this is like a big way of, I mean, lots and lots of things in real life are long pieces of rope or metal that are hanging. So this is a really, really useful area of maths that like kind of comes up. And it also, as I was saying earlier, it's going to connect together with complex numbers and all sorts of areas. So it's like a missing jigsaw piece, hyperbolic functions, that seems to like bridge a lot of areas of maths together. Okay, so we're now trying to sketch what tan x is. And remembering that tan x is sin x over cos x, we're going to try and use the usual, consider the usual features you would do when it is when you sketch a graph. So first of all, what is it going to be when x equals 0? Well, have a look at this that we've got. If x is 0, what would sin x be? And you can look at your graph as well if you need to. 0. And would cos x be, what's cos 1? So you're just going to have 0. So I know that this graph is going to cross here at 0, okay? And I'm going to try and think about what happens at extreme values. So let's just have a think about sin x for a second, because I'm going to see how does the numerator behave as x becomes large, and how does the denominator behave as x becomes large. So because sin x is a half e to the x minus e to the minus x, what happens as x becomes a really big value to sin x? What would happen to either this or this if x becomes really big? This one would get really, really big because it would be e to the power of a big number. What's e to the power of a really negative number? It would get to 0, wouldn't it? So as x goes towards infinity, sin x goes towards a half e to the x, or e to the infinity. But we're just sort of roughly saying, as x becomes a big number, sin x starts looking like this. And as x goes to a big number, what do you think cos x is going to go towards? Cos x is a half e to the x plus e to the minus x. Which of these is going to sort of disappear as x becomes big? No, that's not going to disappear as x becomes big. This one is going to become so small that cos x is also going to go to a half e to the x. So what can you tell me that tan x would go towards?
Also, would be a half e to x.
No, it wouldn't be half e to the x. I thought you were going to say more.
Over 2.
No. Tan x is what over what?
Oh, it would be 1.
Yeah, it's going to be sin x over cos x. It's a half e to the x over a half e to the x, which is just 1. So for extreme values, it will tend towards 1, right? So I'm going to just draw in here. And obviously, eventually, you're going to know what these graphs are, but I want to try and show you like where these things are coming from. So it's going to tend towards 1. And with the same logic, when x goes towards negative infinity, let's think about what would happen to sin x. What would happen to sin x if you put in a large negative number?
Minus e to the minus x would go.
This would be the thing that would be big. This thing here would become 0 and would be negligible and you could ignore it. So it's going to be minus a half e to the x, because it would be a positive number. Okay, not e to the x. I really should have said, I didn't want to use infinity in here, but basically like it's a large number, okay? And cos, what do you think cos would do? It's going to do the same thing as it was doing before because they're both being added. So tan is going to tend towards -1 instead because you've got a negative and a positive 1 here. So that means that you're going to have, for the bottom, it is going to have an asymptote at -1.
So why does cos x do the same thing with infinity?
So if, I shouldn't have used x's here, I'm disappointed by the fact I've used those. But if I put in a really negative number into this bit would be like 0. And if I put in a really negative number for this, it would be a really big number as well. So I suppose I should have just said, I'm actually going to replace this because I don't like the way I've done that. I'm just going to say, I don't know, A, where A is a large number, but it's the same large number in all of those places. Now, what this graph will look like is this.
Yeah, no, doing okay.
Okay, cool. So the than graph has these properties of, it's like sandwiched between the asymptotes at 1 and -1. And do we think that than is odd or even?
Odd.
It's odd, yeah. And the reason it's odd is actually because than is an odd function divided by an even function. And so the odd function makes the overall function become like an odd function, okay? You'll do a lot more about odd and even functions if you're doing maths at uni, because they have lots of properties. And Sam, they'll have properties with Fourier series as well, about making Fourier series a lot easier to do the calculations with as well, okay? So the sketching of reciprocal hyperbolic functions, these are really difficult to think about, but remember you're doing the reciprocal of the y values of these graphs that we've got here, okay? We're going to do the reciprocal of the y values that we've got. So looking at this graph for sin x, are there any places that my graph will be undefined for cosec? Because you're taking the reciprocal of the y values. At the origin, yeah, at the origin, the y value is 0. So when you do the reciprocal of 0, you're going to have an asymptote. What happens when you do the reciprocal of a very small positive number? You get a really big number. And when you do the reciprocal of a really big positive number, you get a really small number. And you're going to get the same pattern, but on the other side. So cosec x, cosec x looks a bit like the reciprocal graph, but with an asymptote at that beginning, at the origin. And so sec x, remember, is the reciprocal of cosh. So at this point here, it's the reciprocal of 1. So it's also going to be at 1. They're going to just touch each other at that point. As you do very, very big numbers, what happens when you take the reciprocal of a big number? It goes towards 0. And as you take the reciprocal of a very large negative number, it also goes towards 0. So you're going to have this kind of like hump kind of pattern, like this.
Is there any relationship between the than graph and the arctan graph? Say, look,
No, because the arctan graph is the reflection in the line y equals x, and the than graph is, if you imagine that graph being reflected in the line y equals x, it would look like a tan graph, but purely just because of its shape, not because if you lay them on top of each other, they wouldn't be exactly the same as each other. It's a bit like how I said that Shine and Cubic looked similar, but they are not at all the same graph. It's just like the shape that we would use to describe it, but a good question. Okay, this one's kind of weird because we're taking the reciprocal of values between 0 and 1. So if you take the reciprocal of 0, you would have an asymptote. If you take the reciprocal of a very small number, you have a very big number. If you take the reciprocal of something that is almost 1, you would get just a little bit bigger than 1. So this graph is going to start up here really high because there's an asymptote, and it's going to come down like this. And then you're going to get the same on the other side. So you get now almost like the graph of cosec, but with like a big wedge in the middle where it can't go. So that coth looks like this. Now you can plot these on your graphics calculators as well, but I think there was something to gain from thinking about like, why are these the graphs? Like, what happens when you take the reciprocal of these numbers? What happens when you try and put e to the x in all of these different places and stuff? Okay, has everyone got those ones drawn? Make sure if you've drawn this one that you do put in the asymptote for this side and the asymptote for this side, because they can't go in this middle section. Okay, so we're going to look at an exam question because there's not many other questions about sketching them. So it says the curve C1 has equation y equals 3 sine 2x, and the curve C2 has equation y equals 13 minus 3e to the 2x. Sketch the graph of the curves C1 and C2 on one set of axes, giving the equation of any asymptote and the coordinates of points where the curves cross the axis. So C1 is going to be y equals 3 sine 2x. In terms of transformations, what is 3 sine 2x? Like, what's happened to sine x to get you 3 sine 2x? There's been a stretch in one direction and a stretch in another direction. How much has it been in the up and down direction? Has it changed? By 3, and in the x direction by a half. So it's not going to look any different, okay? We're just going to, well, it's not even anything to label different for a sine graph when you think about it, because a sine graph normally looks like this. And if I'm going to now stretch it up by 3, okay, well, I've stretched it up by 3. How do I know it looks any different? And if I'm going to squash it in by a factor of a half, okay, well, I've done that too. It's just, how do I know? It just is. It is that is what y equals 3 sine 2x is actually going to look like. Nothing has really changed about it. If I had the original graph, it would look different, but I haven't got the original graph there. Now, the second one is going to be harder to draw. The second one is y equals 13 minus 3e to the 2x. So there's a few different ways of approaching this. I would probably think about it in the same way that I was taught you about sketching modulus graphs, where I just do like a bit at a time. I do some like mini sketches. So I might start off doing a mini sketch of just what does, I don't know, y equals e to the 2x look like? What would y equals e to the 2x look like? Just like a regular exponential graph. And then if I was going to do y equals minus 3 e to the 2x, how would it look different? It would be reflected in the x-axis. It would be going downwards. And can you tell me where it would cross the axis? Yeah, it crossed at 1 here, so it's now going to cross at minus 3 here. And then the last part is that I have added on 13 to this graph. So where will it cross? It will cross at 10. And where would the asymptote be? Where's the asymptote on this graph? Yeah, at y equals 0. So if I'm adding on 13, no, because it crosses at 10. It's going to be at 13. So I'm going to draw on an asymptote here. And I'm going to say this is y equals 13. And I'm just going to draw, it wanted it to cross at 10, didn't it? So I'm going to just draw this. So it's crossing at 10. And it also wants us to show where the curves cross the axes. Well, that one's clearly crossing at the origin. I've said that one's crossing at 10. I've said the equation of the asymptote. But I also need to find out where this one is crossing the x-axis. So there's just a bit of work that needs to be done there. How would I find out where the curve 2 is crossing the x-axis? Set y equals 0. So I get 13 equals 3e to the 2x. 13 over 3 equals e to the 2x. So ln of 13 over 3 is 2x. So x is a half ln 13 over 3. And then we're going to try some questions from exercise 6A that is just going to pull together everything to do with the definitions and a little bit to do with the sketches of these ones that we've got. Okay.